So in this lesson, we are going to go ahead and prove our first of several of Fermat's claims. And so as a reminder, Pierre de Fermat, back in the 1600s, wrote down these marginal notes in his copy of the Fantas Arithmetica. And the grand majority, he did not prove. Actually, he only proved one. And even then, as we will see in the 9th week, when we do go through that result that Fermat proved, his original proof is faulty in the sense that it's not rigorous. So Fermat's little theorem, as it's known, is a statement about the relationship between a prime number and numbers not divisible by that prime. And so what I want us to do is something similar to what we did at the start of Wilson's theorem, where we rediscover the statement by doing some computational examples. So what I want you to do is to choose a prime, so that P be prime, and let A be a natural number such that the GCD of A and P is 1. So A and P are both relatively prime. And then make a table. So you're going to have P, you're going to have A to the P minus 1. And so you're going to be taking A to the P minus 1. Oops, actually, for the table, let me go ahead and just write A over here. And then over here, I want to take A to the P minus 1 minus 1. And what I want you to do is choose a prime P, choose a number that is relatively prime to P, and then compute the prime factors of A to the P minus 1 minus 1. And do this for some P's and some A's. So pause the video, go ahead and do that example. Feel free to use Wolfram Alpha, a calculator, to do the prime factors. Since we're looking at exponents minus 1, these numbers can get rather big very fast. And so pause the video, and when you unpause, we'll go through and look at some examples and see what we get. Okay, so here we have a table. We have 2 and 3. P is 2, 3 is A. And if we do that, then we're just going to get back 2. Because then in this case we have 3 to the 2 minus 1, so just 3, and then minus 1 we get 2. And if we continue doing this, so P is equal to 3, A is 5, we're going to have that the prime factors are 2 cubed times 3, and so our prime P is here, is highlighted. But if we continue doing this for 5, 7, and 11, and we chose in each of these cases numbers relatively prime to those given primes, we see that the prime that we're looking at is always a prime factor. And so this led Fermat to make the following conjecture. If the GCD of A and P is 1, then P divides A to the P minus 1 minus 1. And so that's what Fermat wrote down, and this is what has come to be known as Fermat's little theorem. Now, as I mentioned, Fermat did not prove this. The timeline actually goes back to 1640. And so while it appeared as one of his marginal notes, mathematicians actually learned about the result even before those marginals were published by his son in 1665. So on October 18, 1640, Fermat wrote to Frenicle de Bessy and informed him that he had proven the statement that P divides A to the P minus 1 whenever the GCD of A and P is 1. So A and P are relatively prime. And he actually wrote the following down. And this proposition is generally true for all series. Over here, series is a reference to the numbers A. So it's generally true for all numbers A, and for all prime numbers, But now, the thing I want you to note is this last sentence, because this is common throughout Fermat's correspondences with mathematicians during his lifetime. He would always say something along the lines of what he's writing here to de Bessy. I would send you a demonstration of it if I did not fear going on for too long. So not only was the margin of his Fantas Arithmetica just too narrow, but even the letters that he was writing to mathematicians were just not enough to contain the proofs that he claimed to have stated. And it is for these reasons that when Gauss was asked to consider proving Fermat's theorem, he didn't consider it and even went further to just say that Fermat just came up with his statements. Anyone can come up with the statements Fermat came up with by just applying induction in the sense of doing some examples and believing that those examples extrapolate to a theorem. The hard part is proving it. Thankfully, with Fermat's little theorem, it did not take too long, but it still did take 43 years before a proof was established. So de Vesey was informed about this in the late 1640s. He corresponded with other mathematicians, inquired if they had an idea of how to prove this statement, and no one was able to prove it. And so finally, in 1683, Leibniz actually proved Fermat's little theorem, and we will be seeing his proof momentarily. The thing to note, and this is just a historical side note, if you look at the history of Fermat's little theorem, oftentimes it's not attributed to Leibniz, because Leibniz did not publish his result. He shared the proof with close friends, but it never reached the literature. And so when you fast forward some 50 years later, when Euler was trying to go through and prove as many statements of Fermat's claims that still remained open, this statement Euler believed was still unsolved. And so Euler is credited with proving Fermat's little theorem in 1736, since he published the proof. And so that's the first public proof of Fermat's little theorem. Today we will not be proving it in the manner that Euler did, but in the manner that Gauss's simplification almost 70 years later. And so Gauss, in his Discussiones Arithmeticae, that introduced the language of modular arithmetic, as a cute example of his new theory for modular arithmetic, he proved Fermat's little theorem by basing it on Wilson's theorem, which we proved already in last week, and the theorem that followed directly after, which essentially told us that the integers modulo n, we can essentially multiply by an element a, and so we had this theorem that told us if we had like a times 0, comma a times 1, comma a times 2, all the way to a times p minus 1, where all the elements are congruence classes, then that's always going to be equal to the integers modulo p. So we proved it in more generality. So we're going to be using that result to prove Fermat's little theorem today. And just want to note that I know that it is difficult to follow math spoken out loud. So when we get to the proof of Fermat's little theorem in the way that Gauss did it, I will have the statement for Gauss's theorem so that we can have it in front of us as we quote it. Alright, so let's first discuss Leibniz proof, since that one is the easier form of it. So Leibniz proof relies on what is known as the Binomial Theorem. And so this result dates back to 1000 Common Era, when it was proven by mathematician Al-Khawarizmi. And we have been exposed to this, so we know that over here we have x plus y. If we do this cubed, we have several ways of going about this. One way is Pascal's triangle, and so this is going to give us 3x squared y plus 3xy squared plus y cubed. And we can do also like x plus y to the 4th power. And then here we'll have x to the 4th power, and then we're going to have 4x cubed y plus 6 x squared y squared plus 3xy cubed plus y cubed. Oops, plus y to the 4th, I mean. And now what the binomial theorem is giving us is exactly how this expansion always behaves, but now it's in terms of this n choose j notation. So we can see that for this statement here, if we think about this notation as j equals to 0 to 4 of 4 choose 0, x to the 4 minus j, y to the j. And then the very first entry, 4 choose 0, we're going to have 4 factorial over 0 factorial for the j factorial. That's going to be 1. And then we have 4 minus 0, so we're just going to have 1. And so that's going to be the coefficient there. And so we have that this here is going to be 1 times x to the 4 times y to the 0, so just x to the 4. If you then do the next entry, so 4 choose 1, now 4 choose 1 is going to be 4 factorial over 4 minus 1, 3 factorial, times 1 factorial, and so the 4 factorial is 4 times 3 factorial, so this is going to be 4. And I'll just do one more, 4 choose 2. And so here you're going to have that this will give 4 factorial over 2 factorial over 2 factorial. And so now you have on the top, I'm going to write this as 4 times 3 times 2 factorial over 2 factorial times 2 factorial. And so we can see cancellation with one of the 2 factorials. And so we have 4 over 2 is 2, 2 times 3 is 6. And so we have that this here will be 6, and then x to the 4 minus 1, so x cubed times y. Oops. I forgot to write down the initial one. We're now working with 2, so this here will be 6. Now we're working with j is equal to 2, so we have x to the 4 minus 2, so x squared, y squared. And if we continue, you can verify that we do get back this expansion. Now the binomial theorem, actually its statement is rather interesting. It goes back to India. And so 200 before the Common Era, Sanskrit poet Pingala derived the statement of the binomial theorem as he was using it to uncover how many different ways one can do certain poetry in Sanskrit in terms of the various syllables of having like long and short syllables. And so that's how the statement first arose. The reason that Pascal gets the name associated to it is that he wrote a treatise where he was using the binomial theorem, and oftentimes it was then quoted. And so incorrectly, the binomial theorem is credited to Pascal, even though it had been discovered 600 years prior. In calculus, if you recall, when you prove the power rule, specifically the derivative of d dx x to the n, where n is a natural number, so you prove that this is n to the x to the n minus 1. But if you revisit the proof, the way that this is done is by applying the limit law to x plus h to the n and applying the binomial theorem. And so this is a result that has incredible use in calculus from a theoretical perspective. And what made Newton famous in his work, and why he's usually credited with being one of the major figures in calculus, is that he generalized the binomial theorem to allow real number exponents. And so we can go ahead and have x plus y to the pi, and then have an infinite series that represents it. It's actually going to be an infinite series. And so that's just sort of like a little side note. Now, the way that we are going to be using the binomial theorem is a corollary. And so this is oftentimes called in freshman's dream. So this is the modern name for the following lemma, which I'm going to prove, which is going to be part of how we prove Fermat's little theorem. And before we get to why it's called freshman's dream, it's a reference to one of the common errors in mathematics, at least in earlier courses in algebra. If we have a plus b squared, we know that it's a squared plus 2ab plus b squared, but oftentimes there's the error that it's written as a squared plus b squared. And this, of course, is not true. And then more generally, a plus b to the p equals a to the p plus b to the p. Also not true. But if we work over modular arithmetic, modulo a prime, it actually is true. So let's go ahead and see that. So the statement is, so let p be a prime, then a plus b, and let a and b be integers. So then, if we do a plus b to the p, this is going to be congruent to a to the p plus b to the p mod p. So how do we prove this? Well, we're going to go ahead and apply the binomial theorem. And I should mention, while we are not proving the binomial theorem in today's lesson, this will be part of one of your future quizzes. You'll be tasked with proving this. And the proof is just going to be to go about this by induction. So now, let's prove it assuming the binomial theorem. So we have a plus b to the p. By the binomial theorem, this is a to the p plus b to the p. And now I'm going to go ahead and add then the rest of the terms that we skipped over. So now the sum is going to start at j is equal to j equals to 1. And we're going to stop our sum at p minus 1. And so here we have x to the n to the, we're using a now, a to the n minus j and choose j, and then we have a to the n minus j, b to the j. And so what we want to show is that this here is always going to be congruent to 0 mod p. So in other words, this here is always divisible by p. Now, the way we go about that is making the following observations. So let me go ahead and shrink this. So what the claim is, oops, I just realized I made a small typo. That n should be p. So now the claim is that p choose j is congruent to 0 mod p for 1 less than or equal to j less than or equal to p minus 1. Alright, so if we go ahead and apply the definition of p choose j, so this here is going to be p factorial over p minus j factorial times j factorial. And so that's what we have. But now let's go ahead and write p in the following way. So we know p is just going to be the product of p times p minus 1 times p minus 2, so on and so forth. And you'll also be proving for homework that this is always going to be a natural number. So that's something that I am assuming here, that if 1 is less than or equal to j less than or equal to p minus 1, this is always a natural number. This is going to be part of your assignment. So we're assuming that statement implicitly. So this is going to go all the way until we get to p minus j. And so p minus j is going to appear here. And the term right before p minus j is going to be p minus j plus 1. And then p minus j, and then all the way down to 1. So I'm going to go ahead and just write that as p minus j factorial. And so you have that this here is going to be over p minus j factorial, and so now we have cancellation of the p minus j's factorials, and so what we have is p times p minus 1 all the way to p minus j plus 1 over j factorial. Now, the thing about j factorial, so note that j is less than or equal to p minus 1. So as a consequence, we have that p does not divide j. So p does not divide j, but p is less than or equal to, p is greater than all the values that are less than j. And so what we have here is that p divides p choose j. Because we're never going to be able to cancel off this factor of p. It's always going to be there. Since j is going to be j times j minus 1 times j minus 2, and none of them are divisible by p by virtue of all those terms being less than p. And so p divides p choose j. That's what we wanted to prove, because if p divides p choose j, then we have that this is congruent to 0 mod p. But then if we come back over here and put that statement that we just did and reduce, what we have now is that this is just a to the p plus b to the p plus 0, because here we're going from j equals 1 to p minus 1. And so this is always going to be divisible by p, and therefore we're done. We have our proof. This is always congruent to a to the p plus b to the p mod p. And that concludes the proof of freshman stream. And so that's one of the nice aspects of modular arithmetic, is that we have this result that we can use. And that's going to come in handy when proving Fermat's little theorem in the manner that Leibniz did. So now we're going to go ahead and prove Fermat's little theorem. So we have the binomial theorem, which we will use. The following statement, the lemma 1.10.5, is just reiterating a couple of things we discussed in the last slide. So we have n choose 0 is equal to n choose n, which is equal to 1. If j is greater than 0 and j is less than n, then we have that n choose j is a natural number. We assume this in our proof of the freshman stream, and you will be proving this as one of your homework exercises. And then I have the freshman dream statement over here. if n is equal to p is prime, then p choose j is going to be congruent to 0 mod p. And so here I'm assuming that j is greater than 0 and is less than n. And so that's crucial. But something I want to note is that while we are using the language of modular arithmetic to prove this, which will simplify it for us tremendously, what Leibniz did not have this at his disposal. Recall, modular arithmetic was not introduced until Gauss in 1802 in Discussiones Arithmeticae. So how did Leibniz do it? And it morally is the same proof we are doing, just that we have it much easier by using the fact that congruence is an equivalence relation. So Leibniz approached it in the following way. He started off by setting A is equal to P times Q plus R, so he used the division theorem. And then here, of course, R is the remainder, so R is greater than or equal to 0. Greater than or equal to 0, and less than P. And then when he considers A to the P minus 1, this here is going to be P to the Q plus R to the P minus 1 minus 1. And so he was applying the binomial theorem to this here. And so that's good. That's where our proof differs from his, is that we're going to have it so much easier by working just with the freshman dreams argument, that we can just go ahead and go down one step. So let's go ahead and prove this. So we're going to actually do a stronger statement and then deduce Fermat's little theorem. So proof, let S of A be the statement that A to the P is congruent to A mod P for each natural number A. So that's what we are going to prove. So next, we're going to do the following. So now, let's go ahead and do base case. So S of 1 is true since 1 to the P is of course going to be just 1 mod P. So we're done with the base case. Now suppose that S of A is true by PMI, principle of mathematical induction. It suffices to show that the statement S of A plus 1 is true. So that's where we want to prove that we have S of A plus 1 is true. So let's go ahead and do that. So we have here, so to now consider, write down. So now we're going to observe the following. We're going to consider the statement. So here we're looking at A plus 1 to the P. But now, by the freshman's dream, this is going to be A to the P plus 1 to the P, which is just 1, so A to the P, plus 1 mod P. But now we have that by the induction hypothesis, S of A is true. So A to the P is congruent to A mod P. So A to the P is congruent to A mod P. So this is A plus 1 mod P by the induction hypothesis. And so now that finishes the proof of this statement. So by PMI, S of A is true for each natural number A. Alright, so we have proven this statement, but that's not what we wanted to prove. We wanted to prove that A to the P minus 1 is congruent to 1 mod P. So let's go ahead and do that. So now, suppose that the GCD of A and P is 1. So that was something that we didn't assume up here. We were just letting A be any natural number. By the above, our induction argument, we have that A to the P, and I'm going to go and use congruence classes now. A to the P is equal to the congruence class of A in ZP, integers modulo P. So here we're using the equivalence notions of congruence, and so we're now using the language of congruence classes. Since the GCD of A and P is 1, there exists a multiplicative inverse in the integers modulo P. There exists an A inverse such that A bar inverse times A bar is equal to 1. So what we have now is that by multiplying by the inverse of A in the integers modulo P to both sides, and so here I'm going to write this as A to the, actually I'm going to write this times A. So I factored out A from A to the P, and then we're doing A inverse here times A bar on the right hand side. Well, here we have A bar inverse times A bar, that's going to be 1. A bar inverse times A bar, that's going to be 1. So we are left with what we want to prove. We now have proven that A to the P minus 1 is equal to 1 bar. And that finishes off the proof for Fermat's little theorem. And the benefit is we did it in a nice succinct way and did not have to worry about expanding and trying to figure out what the corresponding remainder was once we expanded it out in this way. And so that's one of the nice benefits of modular arithmetic, is that while we can do proofs that were done in the time of Leibniz and even earlier, they do simplify most of our arguments down to just what is the remainder and deducing the properties of the remainder. And so this is one of the main tools as we go through the term. We're going to be relying on modular arithmetic to prove results. So now that we have this, let us go ahead and do Gauss's proof of Fermat's little theorem via Wilson and his own statement. Gauss's proof is an incredibly nice, clever proof that uses these two results that we have covered. So we say here's Wilson's theorem, and our theorem that followed right after Wilson, specifically that if A bar is in the integers modulo n, such that the GCD of A and n is equal to 1, then this here is exactly all the elements in the integers modulo n. So now, let's go ahead and do the proof of in the way that Gauss went about proving Fermat's little theorem. So we're going to go, our assumption is that A bar is not equal to 0 bar. So by assumption, A bar is not non-zero. So by theorem 1.8.8, actually, so before mentioning that, so just to be 100% precise, so in particular, the fact that it's not divisible by P and P is prime, that tells us that the GCD of A and P is equal to 1. So now we can apply the theorem. So by theorem 1.8.8, we have that the list, or the set, A bar times 0 bar, A bar times 1 bar, that this set here, all the way to A bar times P minus 1 bar, this is just equal to the integers modulo P. It's another way of writing the elements in the integers modulo P. And so this is what Gauss did that makes the proof of Fermat's little theorem follow quite nicely. So let us go ahead and consider the product of all these elements. So we're going to have the following. So we know just to mention that over here, a bar times 0, this of course is 0 bar. And that's going to be the only 0 element in here. So all the other terms are non-zero. And so what Gauss did was to consider the product, a bar times 1 bar, then multiply that times the next one, so times 2 bar, times this times 3 bar, all the way until you get to a bar times p minus 1 bar. But we are just this notation, it looks like different numbers, of course, a times 2, a times 3, a times p minus 1, but this is just by theorem 1.88, this is the integers modulo p. And so over here, we're multiplying all the non-zero elements of the integers modulo p. So this is nothing more than just 1 bar times 2 bar, all the way to p minus 1 bar. So that's what this list is. But in this list, on the left-hand side, oops, did not mean to erase. So on the left-hand side, how many a's appear? So we have a here, a here, a here, and a here. So we actually have p minus 1 copies of a. By commutativity, the integers modulo p is a ring, so we can commute. So we can go ahead and multiply this a to that a, we have a squared. Multiply that a to the corresponding a squared that we just got, a cubed. And doing so gives us a to the p minus 1 bar. And then we have 1 bar times 2 bar times 3 bar, all the way to p minus 1 bar. And so we have this here. But on the right-hand side, we just have 1 times 2 times 3, all the way to p minus 1 bar. This is just p minus 1 bar factorial. And so we have this here. Now, p minus 1 bar factorial is a non-zero element, and we know by Wilson's theorem that it's congruent to -1. Also, you don't have to use Wilson's theorem here at this point. I'm going to be using it, but just notice that because p minus 1 bar factorial is not divisible by p, so it's going to be non-zero, we have that it has a multiplicative inverse. So we can go ahead and multiply both sides to get back 1. And so that's another way that we can do this. I'm going to go ahead and use Wilson's theorem. So we have -1 bar equals -1 bar by Wilson's theorem, which is really not needed for this, as I mentioned. Multiplying by -1 to both sides, we have that a bar to the p minus 1 is equal to 1 bar. And we have proven Fermat's little theorem. And so the nice thing about this proof is that in the next lesson, we are going to generalize Fermat's little theorem, a theorem that was proven by Euler. And what we will see is that this argument of Gauss actually carries over to a generalization of Fermat's little theorem in a way that the argument of Leibniz does not. So here is a restatement of Fermat's little theorem. So we can also we just proved it in terms of the language of working in the integers modulo p. So we're using the congruence classes. If we restate it in the language of modular arithmetic, we just have a to the p minus 1 is congruent to 1 mod p whenever a is not divisible by p. For homework, I'm going to ask you to prove that a to the p is congruent to a mod p. Of course, we have already done this. We proved this via induction in our argument for Leibniz, in Leibniz argument. But what I want you to do for the homework assignment is to prove this by using Fermat's little theorem. So notice that we didn't prove that claim over here. And so now I want you to deduce a different proof for this result for your homework. So for our next example, we are going to do some computation for Fermat's little theorem. So let's go ahead and suppose we want to find 43 to the 38 modulo 37 by hand. Well, this looks awful. we're raising something to the 38th power, but Fermat's little theorem and the properties of modular arithmetic will allow us to simplify this significantly. Here's how. So we look at 37, so we know that that's what we're modding out by. That's prime. So by Fermat's little theorem, which I'm going to write as FLT with a lowercase l for little, whereas with Fermat's last theorem, we usually write the capital L in between the F and the T. So by Fermat's little theorem, we have that a to the p minus 1 is congruent to 1 mod p for p not dividing a. And so that's what we have. Now here, that's not exactly what we were looking at, but we can go ahead and break this down. So let's look at 43. This is equal, so 37 minus 1 is 36. So let's write this as 36 and then plus a 2 here. So of course, this will be 43 to the 36th power times 43 squared mod. And then we're going to reduce modulo 37. So by Fermat's little theorem, 43 to the 36 is 1. So we're just left with 43 squared mod 37. But now 43 squared, we don't want to go ahead and do 43 squared. We instead want to ask, what is 43 modulo 37? And in this case, we have that 43 is going to be 6. So we can go ahead and replace the 43 with a 6. And now we have that that's 6 squared modulo 37, since 43 is congruent to 6 mod 37. And now this we can actually do by hand. We have this is 36 mod 37, and that concludes it for exercise 10.1. We just went ahead and did this by hand for this question. And so this is the approach you want to keep in mind for some of the homework questions in the section for Fermat's little theorem, which will have you compute these things by hand. And it's just doing these tricks. So for the next exercise, we're going to be looking at two distinct primes, p and q, and we want to prove that p to the q minus 1 plus q to the p minus 1, that is always congruent to 1 mod p times q. So how do we do this? So let's go ahead and consider the congruence given. The left-hand side of the congruence. So we have p to the q minus 1 plus q to the p minus 1. And now we're going to reduce this mod p and then q. So we reduce mod p, and we're then going to reduce mod q. So if we reduce mod p, p to the q minus 1 is always going to be divisible by p, because q is going to be at least 2. And so this is never going to be 0. It's always going to be a positive integer. And so now we have that then, that's going to be, so if we reduce mod p, this is 0. And so we're just left with q to the p minus 1. And similarly, if we reduce q to the p minus 1 plus p to the q minus 1 mod q, this is 0. And so we get, that's p to the q minus 1. But now Fermat's little theorem comes in and tells us that in both instances we get 1. So we get 1 mod p and 1 mod q by Fermat's little theorem. But now we use the Chinese remainder theorem, well, specifically the corollary of the Chinese remainder theorem. So what we have is that p to the q minus 1 plus q to the p minus 1, that's what we're taking to be our x. In both cases, we have that that's congruent to 1, and so y is taking the role of 1. And then we're modding out by a, p, and then b here is q. And so by the corollary, 1.9.3, we deduce that then p to the q minus 1, which is what we are taking to be our x, that this here is congruent to 1, which is our y, mod a times b, which is our p times q. And that finishes it for this exercise. So where do we go from here? So as a reminder, Euler proved Fermat's little theorem in 1736. And so now the question that he asked following his proof of Fermat's little theorem. So as a reminder, Leibniz, while being the first to prove Fermat's little theorem, he did not publish. So in Euler's eyes, he was the first one to devise a proof. And from that moment onward, he asked, can we generalize Fermat's little theorem and get something more general that does not just apply to modulo a prime, but modulo a composite number. So let us try and follow in his footsteps and uncover how such a generalization of Fermat's little theorem would be. So at its core, Fermat's little theorem is saying that if we have a to the p, that we have a to the p congruent to 1 mod p if p is prime, and 1 is less than or equal to a, less than or equal to p minus 1. So that's one way of viewing it. Also that the GCD of a and p is equal to 1. And we're going to come back to that statement in a moment. So a generalization, a possible generalization, would be fix a natural number n. And what we want to know is, does there exist a natural number m such that if we raise a to the m, we get back that this is congruent to 1 modulo that number n for each a that satisfies the inequality 1 less than or equal to a less than or equal to n minus 1. And so that seems to be the a way of generalizing Fermat's little theorem. But is this a true statement? Pause the video and think about it. Is this true? So now that you've had some time to think about this question, we actually have that it's false. And we have seen some examples where we have the zero theorem fail. So what if we take 2 squared? Then this is of course equal to 4. But if we're modding out by 4, then we get that this is 0. And so this can never be congruent to 1. And so right there tells us that we should not expect this statement to, well, this statement is just going to be completely false, counterexample. So we now need to find a way of fixing it if we want to make a generalization for Fermat's little theorem. So I'm going to go ahead, this is false. So let's go ahead and try again. So generalization attempt. Number 2. So we're going to fix a natural number n. And now we want to ask, does there exist a natural number m such that a to the m is congruent to 1 mod n whenever the GCD of a and n is 1. So now this is the right successor to Fermat's little theorem, because every element that in here, 1 is less than or equal to a, less than or equal to p minus 1, is relatively prime to p. And so this is the statement that we want. And so, is this true? Because we just saw that this one is not true, so we also have to check if this is even a true statement. So what I want you to do now, and I'll get you started, is we're going to fix a few natural numbers, so that are composite. Fermat's little theorem tells us the case when it's prime, so we only have to look at the composite numbers. And so let's go ahead and look at 4. The next composite number after 4 is going to be 6 and 8. And if you want, you can also do 10. And what I want to ask is, over here in the second column, we're going to have m, where we have that m satisfies that a to the m is congruent to 1 mod n for each a satisfying that the GCD of a and n is 1. So let's go ahead and see how we will go about this. So if we look at 4, we first have to look at what are those numbers relatively prime to 4. And so we're looking at those GCD of a comma 4 is equal to 1. Well, we're working with congruence classes, so we don't have to go to say 5, 10, or numbers greater than 4. We just have to look at a being between 1. So we're only looking at those a's that are between 1 and 4. And in fact, 4 that's not going to be relatively prime, so 3. So with that in mind, we have that the only possibilities are 1 and 3. So now we want to ask, can we raise it to some power and get back 1? So of course 1 is a possibility for 1, but 3 to the 1 is not congruent to 1 mod 4, so m is equal to 1 is not possible. Let's do m is equal to 2. 1 squared is 1, so that works. 3 squared is going to be 9, but 9 is congruent to 1 modulo 4, so we have a candidate. And so we have that here, 2 works. So now what I want you to do is do the same argument for 6 and 8, and only write the first m that you find. Don't worry about going through all the possibilities. Just write the least value of m. So just try it out and see what you get. So now, I've gone ahead and done the same, going all the way to 15 for our composite numbers. So on the right hand side, we continue. So we did a comma 4 together. We have 1, 3. If you did 6 and 8, you see that 1 and 5 are the only numbers relatively prime to 6. For 8, we have 1, 3, 5, 7. If we go, say, down to 15, we have that there are 8 numbers that are relatively prime to 15. But now, note the following. If we go ahead and look at 6, and we raise everything to the second power, 1 squared is 1, 5 squared is 25, which is congruent to 1 modulo 6. So we have that 2 is our desired m. If you go over to 4, then you have 3 to the 4th power is going to be 81. But you're reducing modulo 8, so you get that that's congruent to 1 mod 4. 1 mod 8. And you can go ahead and check that 5 to the 4, 7 to the 4, those are also going to be congruent to 1, so that's going to be a candidate. If you go over to 15 with a calculator, you can go ahead and verify that raising each of these numbers, which are the only ones relatively prime to 15, to the 8th power, is going to be congruent to 1 modulo 15. And Euler came up with this conjecture soon after proving Fermat's little theorem. But, we have only done a handful of examples. We only went down to 15. There's infinitely many composite numbers. If this had been Fermat would have already made a marginal note and said, I have a proof for this theorem, and have not done it. But thankfully, Euler is not Fermat. And Euler actually worked at this for a long time to be able to prove it. And over the course of the end of today's lesson and the next lesson, we are going to follow in the footsteps to prove Euler's generalization of Fermat's little theorem, which Euler proved 27 years later. So generalization in 1763. So it would take him 27 years to generalize and prove Fermat's little theorem. And that's because we will have to develop some machinery and language to be able to prove this result. So for example, what we can see in the pattern, and this is what we will be proving with Euler's theorem, is that if we want to write a nice clean statement for a generalization of Fermat's little theorem, we really have to count the number of elements that are relatively prime to a given n. And so we're going to go ahead and call that phi of n. And we'll study this in further detail in our next lesson. So number of elements a var in the integers modulo n such that the GCD of a and n is 1. And so this is the Euler phi function. And what Euler proved is that if you have a to the phi of n, then this is congruent to 1 mod n whenever the GCD of a and n is 1. And so this is Euler's theorem, which was proven in 1763 and will be the focus for the rest of today's lesson, and the next lesson we will actually prove Euler's theorem. So let's go towards that direction. So the first thing we want to do is develop the language for stating phi of n. And we're going to go ahead and give a new name to something we've already been discussing. Those numbers relatively prime to n. So far we haven't assigned them a name. We just call them the numbers relatively prime. 1 and 5, 1, 3, 5, 7. We're going to go ahead and now call those reduced residues. And so by a reduced residue of the integers modulo n, we mean the congruence class of A such that the GCD of A and n is equal to 1. And so that is all we mean by a reduced residue. It's just that when we're working with the integers modulo n, we have that they are relatively prime. So notice that we've already talked about this. So a consequence of this from previous lesson we can go ahead and now state the following equivalence. So we have already shown that a bar in the integers modulo n has a multiplicative inverse. If and only if the GCD of A and n is 1. Well, we're now defining reduced residues, and so we can just say that it has a multiplicative inverse if and only if a bar is a reduced residue. So we're introducing a new word, but it's nothing new. We've already been working with this terminology for a couple of lessons now. So whenever you hear reduced residues, keep in mind we are talking about those elements relatively prime to n. So now we are going to prove that reduced residues are well defined. And so specifically, we're going to be proving that if n is a natural number and a and b are integers such that a bar is equal to b bar in the integers modulo n, then if a and n are relatively prime, then so is b comma n. So let's go ahead and prove this. So what we're going to do is let d equal the GCD of b and n. And I should note, in the textbook there's a different proof of this. The book does this by contradiction. I am going to go ahead and do a direct proof. So we have d is equal to the GCD of b and n. Since a bar is equal to b bar in the integers modulo n, we have the equivalent conditions for congruence, theorem 171. There exists an integer k such that a is equal to b plus n times k. Now, we observe that d divides b and d divides n by assumptions is the GCD. So the linear combination lemma, we deduce that d divides a. But if d divides a, so since d divides a, and by assumption d divides b, divides n, that's what we want. By assumption d divides b and d divides n, but we're going to be looking at the d divides n part, we have that d divides the GCD of a and n. by assumption, or by definition, D is the GCD, so it's greater than or equal to 1. And therefore, since by assumption the GCD of A and N is equal to 1, we conclude that D is equal to 1. And that finishes up this proof. And this is really just a consequence of having equivalence classes for congruence that just give us the remainder. And so now we are done with this statement. So now we know that if A bar is a reduced residue, then any other representative, specifically B bar, is also a reduced residue if they are the same congruence class. Now that we have established that reduced residues are well defined, we are going to go ahead and assume the following lemma. And so this is that reduced residues are closed under multiplication. That is, if we have two reduced residues, we multiply them, we get back another reduced residue, namely A bar times B bar. So you will be proving this as part of your homework assignment in section 9.2, number 3. And so what we are going to do is actually generalize the theorem of Gauss to reduced residues. So we're going to go ahead and fix a natural number n, and let A bar be a reduced residue in the integers modulo n. And now let us suppose that we can list out all the reduced residues of the integers modulo n, and that list will be n1 bar, m2 bar, all the way to mk bar. And these are the distinct reduced residues of the integers modulo n. And what the statement is saying is that if we multiply A bar times m1, A bar times m2, all the way to A bar times mk, that this here contains every reduced residue of the integers modulo n exactly once. So in other words, multiplying by A bar just rearranges the reduced residues. And so this is an extension of what Gauss showed. So what we are about to prove actually is nothing new. In theorem 1.8.8, we actually already have covered this. We know that A bar times all the elements over here contains every element of the integers modulo n exactly once if and only if the GCD of A and n is equal to 1. And so if we have reduced residues, they multiply, we get back another reduced residues. So what we are doing now is specializing to the case when this list only consists of the reduced residues, and then multiplying by A bar, where A bar is a reduced residue. So this is just going to be a consequence of this theorem, but we're going to go ahead and give a new proof of it, but it will be essentially the same proof that we have here in front of us in disguise. So let us go ahead and now prove this corollary in a different way, even though, as I mentioned, it is a consequence, a rewriting of Gauss's theorem. But let's go ahead and prove this. We're going to do it by contradiction. So towards a contradiction, suppose that the list star does not contain every reduced residue of the integers modulo n exactly once. Now, the lemma that we are assuming, lemma 1.11.2, which will be part of your homework, that tells us that A bar times mj is always a reduced residue of the integers modulo n for 1 less than or equal to j less than or equal to k. So we have this here. The contradiction assumption is telling us that this here does not contain all the reduced residues of the integers modulo n exactly once. So that's not being satisfied. So that means that if we look at this as a set, the order a set, so by assumption, we must have a repeat. So if we look at the set of A bar times mj less than or equal to n, this has to be strictly less than k. Oops, wrong one. So this has to be less than k. So this notation I'm using here, this is the number of elements in the set. And of course, if it was equal to k, then we must have all the distinct reduced residues, because the assumption is that m1, m2 to mk bar are the distinct reduced residues. So there are k distinct reduced residues in the integers modulo n. So if this set was exactly equal to, if the number of elements in this set was exactly equal to k, then that will contradict our assumption that this list does not contain all the distinct reduced residues of the integers modulo n exactly once. So this is less than k, but if it's less than k and they are all reduced residues, that means that we must have a repeat. So as a consequence, we have that A bar mj bar must equal A bar mt bar for some j not equal to t. But now A bar is a reduced residue, so it has a multiplicative inverse. So since A bar is a reduced residue, A bar inverse is in the integers modulo n. Now if we multiply both sides of this equation, we get A bar inverse A bar mj bar is equal to A bar inverse A bar times mt bar, which then is equivalent to saying nj is equal to mt bar. But that's a problem, which contradicts your distinctness. The assumption, and we're done. Because by assumption, each of the mj's are distinct. And now we have shown that we have two of these reduced residues, distinct residues being equal. And so that is a problem, contradiction. The proof is over. And now we have done our beginning steps to proving the generalization of Fermat's theorem. And so in the next lesson, we're going to go ahead and prove Euler's theorem. And so 27 years of work compressed into one lesson.